Hello, welcome to my channel. In this video we will continue solving some examples about how to draw the shear force diagram and bending moment diagram. In the previous two videos, we solved two examples about a cantilever beam with a point load and a simply supported beam with a distributed load. In this video we will solve cantilever beam with a distributed load like this. Okay, the length of the beam is 3 meters, and this is 2 kilonewton per meter. 2 kilonewton per meter means this length is 2 kilonewton per meter. Okay. Okay, so let's start with the first step. Step 1, calculate the support reaction. And in this case, we have a fixed beam, a fixed support with this distributed load. Mm-hmm. 2 kilonewton per meter, 3 meters. And you have a support action Fy, Fx, and moment Mz. Okay, solve the equation of equilibrium to find the support action. Okay, so summation Fx equals 0. That means Fx equals 0. Okay, and then summation Fy equals 0. That means Fy upward minus the equivalent point load to the given distributed load, and this is pointing downward, so that's why I added the negative sign here. But the question is, what is the value of the point load equivalent to this distributed load? And as I mentioned in the previous video, to calculate the equivalent point load to a given distributed load, whatever the shape of this distributed load is, you will calculate the area of this distributed load. So this distributed load is a triangular shape, and the area of a triangle is half times the base, which is 3 meters, times the height. In this case it is 2 kilonewton meter. This is the height and this is the base length. Okay, so half base times height. This is the area of a triangle, and this should be equal to 0. That means Fy equals 3 kilonewton. Okay, the moment, summation moment about z equal to 0. That means we have mz. Okay, and I will take the moment about the hinge point itself. So mz is positive because it is counterclockwise, and then the moment produced from the distributed load would be clockwise, so it would be negative, and it would be the point load equivalent to this distributed load, which we just calculated in the previous step, which was 3 kilonewton. Okay, from here. Okay, times the distance. how much is the distance between the point of action of the point load equivalent to this distributed load to the hinge. Again, this point load is applied to the centroid of the shape for the distributed load. So the distributed load is a triangular shape. The centroid of a triangle is right here. This distance is 1/3 times the base length, which is 3. So it is 1. Let's make it a little bit bigger. Oops. So this should be somewhere here. So this is a point load, which is 3 kilonewton, and it is acting at 1 meter from here. Okay, then it is 3 times this distance, it is 2. Okay, this should be equal to 0, and that means mz is equal to 6 kilonewton per meter. Okay, let's move to step 2. Step 2 is to find or get the shear force and bending moment functions. Okay, so we have, this is the beam, and here is the distributed load. And now you know the moment right here is 6 kilonewton meter, and support reaction is 3 kilonewton, and that was 2 kilonewton per meter, and the length was 3 meters. And then we got the point load equivalent to this distributed load right here as 3 kilonewton acting at this point at a distance of 2, right? Okay. To find the shear force and bending moment functions, we will do a cut. Let's do the cut right here, anywhere between the starting and ending point. So the left side of the beam will look like this. We have, this is 3 kilonewton, this is 6 kilonewton meter, and this is a distributed load, and we have, this is x, right? these are all the forces we have. But the question is, how much is this? How much is this height is? In the initial problem, we have 2 kilonewton per meter, and this is at x equals 3 meter. In this case, we want to know how much is this for any value of x. So to calculate this, it is equal to 2 over 3x kilonewton per meter. Okay, 2 over 3x. In case of x equals 3, this will give you 2 kilonewton per meter, which is the original distributed load. Okay, so we have the shear force here, V, and moment, M. Let's move this a little bit up so you're not confused between. Okay, so this was 2 over 3x kilonewton per meter. Okay, and then solve the equation of equilibrium in the y direction. Summation Fy equals 0. That means the 3 kilonewton, this one is upward, minus V, the shear force is downward, minus the distributed load, and as we said, to calculate the equivalent point load, it will be the area of this distributed load, so half times the base, which is x, half x, times the height. In this case, the height is 2 over 3x. Okay, this should be equal to 0. Then that means the V is equal to 3 minus x squared over 3. Okay, so this will be the equation for the shear, 3 minus x squared over 3. Okay, now the time for the moment. Summation moment about z is equal to 0, and take the moment about this point, the cut point. Okay, so we have m, and then we have the 3 kilonewton, and this is negative 3x, and we have positive 6 kilonewton meter, and we have negative, the distributed load is 2 I think we got the equivalent point load in the shear equation, this one, and it is acting right here. So this is x squared over 3, and it is acting at this point. So this distance is x over 3. Okay, so that means it is negative x squared over 3 times x over 3. and this is equal to 0. So the moment would be this is x cube, right, over 9, and then plus 3x and minus 6. And this is the equation for the moment. And the third step is to draw shear, force, and bending moment diagrams. Start excuse me, start with the beam, and distributed load, okay, 2 kilonewton per meter, distance is 3 meters, okay. And let's see, this would be for the shear, and this would be for the moment. Here is the shear, V, and here is the moment, M. And you remember the equation for the shear was V equals 3 minus x squared over 3, and for the moment x cubed over 9 plus 3x minus 6. Sorry. Okay, so let's start drawing this at x equals 0. The shear will be x equals 0. That means shear equals 3 kilonewton. At x equals 3, then it will be 0, right? And you will connect these 2 points with a parabolic shape, x squared, okay, x squared. And actually the maximum point for this will be the 3 kilonewton. So you will do something like this. And this is not a straight line, it is a parabolic, but yeah, for the moment equation at x equals 0, you will have moment equals -6 kilonewton dot meter. And for x equals 3, so this would be 27 over 9, which is 3 plus 9 minus 6, right? So this should be 3 plus I think we forgot a negative sign here. Let's go back to the equation of the moment. for the moment of the distributed load, for the moment of the distributed load, it is positive, not negative, because it is counterclockwise. Okay, so that means that this would be negative. And going to the equation here would be negative. So in for sure the same will be for x equals 0, but for x equal 3, so this will be negative 27 over 9, negative 3 plus 9 minus 6 is 3, this will be 0. Okay, so this will be 0 right here, and the shape will be x to the power 3, so it should be look like this. Oops, sorry, it should be look like this, faster than the x square. Okay, the question is, how did I know that I did a mistake in the equation of the moment? This is a very important point to catch your mistakes while solving this kind of problems. For cantilever beam, you have to have 0 moment in the free edge. Okay, so this is the free edge at x equal 3. So the moment must be 0 at this point. If you got any number different than 0, then look for your mistakes. Okay, I hope this was helpful.